So, surprised to see me. John is busy being external examiner somewhere, so I'm back. But I don't know if I'm lecturing next week or not. We'll have to wait and see what happens. Last time we spoke, we were discussing the innards of the operational amplifier, and we actually started dealing with the DC conditions, but I want to go back and do that again, because it was right at the end of the lecture, and it tends not to sink in quite so well, and I'm also a bit tired, and it can't hurt to do it twice. Not this. Come on. Maybe it would be better if I just put the notes on the iCloud and you could all just steal them. There is a long delay between me pressing the button and the slide changing. We just have to wait. While that does change. So in this lecture, there it is. In this lecture we will be looking back at the op-amp. It's 3 stages, and we will talk a bit about the DC conditions. And then we will consider the differential amplifier, which is the bit that subtracts the 2 signals, the inverting and non-inverting input. And then we will go and have a look at the so-called voltage amplifier stage. It is not, in fact, responsible for all of the voltage amplification, but the majority. People tend to gloss over the fact that the differential amplifier has a gain as well, a voltage gain which may be bigger than 1. And then we'll look at the output stage, and then we'll talk a bit about amplifier classes and angle of conduction, that sort of thing. So we've seen this diagram before. It was in the end of the last set of slides as well. We have 3 stages. Got my lightsaber. So input stage, which is a differential amplifier. These 2 transistors share a tail current, which gets split up evenly between IC1 and IC2. Ideally evenly. It's your business as the designer to make sure it is even. And if you don't, then the operation of the stage will not be optimised. You'll have different base currents, lots of weird stuff which you can read about if you want to. We've got a common emitter with no degeneration, no resistor here, which is loaded by RVA, and this essentially takes you can think about it as accepting a signal current here and producing a bigger signal current here, with the gain being beta times some factor. Or you can think about a small voltage change here, controlling a bigger current change here. It's your choice, either works well. If you want to think of it as current in, voltage out, you'd have to call it transimpedance. If you prefer to think of it as voltage in, voltage out, then it's just a voltage amplifier. They are equivalent and the same, and it's all just a matter of how you think about it. We then have some output stage, which is an emitter follower and an emitter follower arranged so that Q4 does half of the sets of waveform and Q5 does the other half. And we'll look at that right towards the end of the lecture. And if we think back to EEE225, we said that an op-amp is kind of like this. It's got something which does subtraction of 2 signals, something that produces an enormous amount of gain, and then something to drive a big output current, or a big-ish output current. So that's how the stages break down. The feedback, which is not drawn, we usually have a resistor from, say, there to there, and another one from there to the ground, and that would produce a non-inverting amplifier. Feedback is to the V- node. This is our input node. You could sort it so that it's the other way around, and you could make an inverting amplifier, and that would work equally well, and it would be the same analysis that we did in 118. So those are the 3 stages. So as I said, op-amps won't work properly without feedback. Feedback is such a confusing topic. It's subtle and brilliant, and always surprises you. Always surprises me anyway. And it's a wonderful thing to see it working, because it seems like it shouldn't. It always seems like it shouldn't. And when you see it and you think, it's all perfect and it sorts itself out and it's lovely, and electronics is fantastic. But when it doesn't work, it's a complete bitch to debug, because you've got to sit there and go, well, the voltage on this node is wrong, and that gets sent back to here, which affects the voltage on this node, so where do I start? And of course you can't just break the feedback, because then you get an enormous open loop gain. But that's the case. If you've been in the amplifier lab and it hasn't worked perfectly first time, which is fairly likely, then you will know what I mean. So if the non-inverting input and the inverting input are both equal to 0 approximately, then VE1 and VE2 will be 0.7. And the reason for that is, if I said this point's going to be at 0, I'm going to have 0.7 across this base emitter junction, so this business here should be at plus 0.7 volts. So IE will be VS, let's call it 15, minus 0.7 divided by RE, which apply Ohm's law to RE. And then we'll assume that the current splits evenly between the collector of Q1 and Q2. So IC1's half of IE, and we know there's 0.7 volts across that, so there must be 0.7 volts across that. We already know what this current is, it's half that current, so you get R1 by Ohm's law. Happy? One happy. One happy and the phone's going off. Hang on. Yeah. Deal with it later. Want to hear that again? Yeah? So, this is the skill of the engineer. To sit at the circuit and go, what do I know? Let's apply Ohm's law. 0.7 here, here and here. Bang. Of course, if you apply the 0.7 in the wrong place, or you say I is R upon V, it's so hard for me to get it wrong, because it's built in. Yeah, that is wrong. Then you will come up with a load of nonsense, and it will sound just as good as if it's right. So it's something that needs practice. So we got, if this is 0, and all these transistors, all the transistors in their forward active region, I should have 0.7 volts across this base emitter. Doesn't matter that it's PMP, it just means that the emitter will be above the base, whereas for MPN, the emitter will be below the base. Yeah? No. If I've got a NPN transistor with some stuff around it I don't care about, if it's in forward active, this should be 0.7. Base bigger than emitter. But if it's PMP, I'll try and draw it the same way up. I should have that way around to get this also in forward active region. But in that particular diagram, this is drawn flipped on its x-axis, or mirrored in x rather. Happy with that? You could make this op-amp circuit out of NPN transistors, and if you wanted to do that, it would look it's a little man or woman with two eyes. There's no, there you go. Done. So if we wanted to switch this about so it was all out of NPN, you could arrange it like this. I will move in a second so you can see what's going on. So this is, oh, inputs there, and that goes around there, and this is the, so they're equivalent as well. Are you resting your hand on your head, or you want to ask?
You said that like voltage source, then there'd be voltage displaced correct to RE, and then 0.7.
Yep.
and then another 0.7.
Yep.
So should it be 1.4 above Q1 and Q2? I'm not.
No, because the question asks, sorry, I can't find it, there it is. If there's 0.7 there, shouldn't we have 0.7 there? And if that's the case, shouldn't this be 1.4 volts above the ground? The answer is no, and the reason is this: we've got 0 here and we go up by 0.7, so we're 0.7 above the ground, then we've got 0.7 there. So arrowhead on this end, arrowhead on that end, so we've gone up 0.7, and then we go back down 0.7. So both of these are ground. Happy? Or no? I need a bigger bit of chalk. Ignoring the fact this is the other way around, your question still stands. I've got 0.7 volts there. So this is at minus 0.7 now, at that point. And then I've got another 0.7 there. So I've gone down 0.7, then I go back up 0.7. So if I ground that, this one should also end up at ground. Happy?
Yeah.
Ish. Ah. So after the, we're at the point now where we've got VA, and assuming there's some feedback, and we don't put any signal in, there shouldn't be any current in the load. And if there's no current in the load, there can't be any voltage across it, because it's a resistor and Ohm's law applies. If there's no voltage across it, this point must be at 0. And we'll assume these two are both switched on. So there's 0.7 there, with this being 0.7 above 0. And we'll assume this is 0.7 below 0. Now, the fact is I've said that's plus 0.7, that's minus 0.7. They're clearly connected together. So actually I've told you a little bit of a lie. But towards the end of the lecture, you'll see why I did that. We could just assume they're both switched off, but it doesn't really help the analysis, even though they are. So let's assume there's a magic box in here that allows that to be 0.7 volts, or 1.4 volts above that. These both turned on, 0 volts there, you're going to have minus 0.7 there. And if you've been in the amplifier lab, or you do it in the next couple of days, this will look very familiar. So what I've said on the slide is, on this slide that you see now, is pretty much what I've been rattling on about for the last 5 minutes. The only thing that I haven't said is the bottom bit. In the case where V plus and V minus, so inverting and non-inverting input, are both not equal to 0, so they're both going up and down together, then that's called a common mode input, because it's common to both inverting and non-inverting terminals. The effect of that is that, well, we can see the effect of it. Let's go back over here. If I made that plus 1, and I made this plus 1, so they've both gone up together, this point here is 0.7 volts below 1, instead of 0.7 volts below 0. So this should now be at plus 0.3, is it? 1 minus 0.7. If it's at plus 0.3 and this is at minus 15, the voltage across this resistor, which is the same as the one at the top of it's not on the screen, this voltage increased slightly. So the current that flows down there will increase slightly. So this current in here will increase slightly, current in here will increase slightly, half as much as the increase there. The voltage drop across here increase slightly. This transistor turn on a bit more. This current increase a bit. Voltage across there drop a bit. These two move down in voltage because this voltage is getting bigger. Sorry, up. These two must move up in voltage because there's something here which is taking up more voltage. These two moving up in voltage. This one turns on more. This one turns off more. Current flows through there. No, I didn't draw a load. The current down there like that. Same arguments apply. If I did minus 1 there, it would all go in reverse, and the current would do that instead of that. There is no amount of times that I can stand and say it. Also, you can just watch me say it again and again and again till you find all the mistakes. You've just got to practice a bit. If you want to see that exact circuit, it's in Horowitz and Hill, chapter 2 or chapter 3. But you can find it in lots of textbooks. It's very common. So if we look now just at the initial part, the differential amplifier, and we will look at a differential mode signal. So they're not going up and down together. When one goes up, the other one goes down. Or at the very least, when one goes up, the other one doesn't change. So there's a difference, because it's the difference we're going to amplify. But here I've gone with up and down. So VI plus is a non-inverting input, and VI minus is an inverting input. And I said that VI plus, so non-inverting input, goes up by a small amount, delta V. And that VI minus, inverting input, goes down by a small amount, delta V. This will cause this transistor to turn off a bit, because this is still going to be at plus 0.7-ish, assuming that VI is not much, and this is, like I say, this is 0, and it's plus a very small amount. This will turn off slightly, because this is still at 0.7, so this voltage has gone down, because this point's got bigger. Happy? Happy? Want a biscuit? Come on, it's like gone 11, even I'm awake. On the other hand, this potential's dropped a bit. So this VBE junction's got a bigger voltage across it, because this is still more or less fixed. This has dropped, so this voltage got bigger. As a consequence, this transistor turned off a little bit, because the VBE's got smaller. So the current that flows in the collector will drop a bit. So it'll be half of I, we've already said it's split evenly, under ideal conditions, minus a small delta I. And just for completeness, because Q2 is turned on a bit more, we have the I by 2 from there, half, plus a small delta I. And if the transistors are the same and everything's ideal, this delta I and this delta I will be the same size, so the current just gets sort of steered one way or the other. And as a result of R1 being there and this current getting slightly smaller, VR1, or sorry, VOut is now minus delta I times R1. I've ignored that. But it's Ohm's law across that resistor. Happy? Yes?
But if it's gone below 0.7, why does it turn off completely?
Hasn't gone very much below 0.7. We are talking about only a small change. So the question, just in case you didn't hear the question, have a biscuit for a good question. You've been looking after this. I suppose you want biscuits looking after this, isn't it? I can ditch this, yeah? Actually, I'm going to go over there because it can show up bigger. So if I got just a single transistor on its own, and let's imagine we so I'm going to run a test, and I'm going to change VBE while I keep EC more or less constant. More or less constant. The resulting graph that I will draw will be a transfer characteristic. So I'll end up with VBE against IC. So I'll measure this current. And I'm going to get something like that, where this is exponential. IC is, where are we? E to the QVB E on KT minus 1, brackets, IC 0. So this is exponential, and what we're saying is that I was here at 0.7, and I'm not going to move sufficiently far down this way to make this current very small. I will only move a tiny little bit. So if that was maybe a milliamp, I will move it so that it only goes down to say maybe 0.990 micrams. So that's 1% change. This is a very small change. And what you're saying is correct, if we had a big enough change, the transistor would turn off. But we are talking about just a small signal. So when I say small, I'm talking 1% or so. Of course, if it was a transmission line and we were sending power between France and Britain, a small change could be 10 kiloamps, but if it's on a megaamp, it's still only about 1%. So it's relative, and towards the end of today, that relativeness will become clear. Happy? You better send in the biscuits for looking after my ball brother. So what did I miss? If V plus and V minus increase or decrease by delta VI, VI is called common mode signal. I've talked about common mode signals already. So that's if they both go up and down together. We will not come across common mode signals again, but if you look at a data sheet for an op-amp, it'll give you a number called the common mode rejection ratio, which is the amount of gain you get for a common mode signal. Obviously you want none, but you don't get none, and they're not perfect, so you ought to at least know that. The top bullet point is if you've got a, well, that's also common mode. God, I was really obsessed by common mode when I wrote these slides, wasn't I? Must have been on the telly or something. So, when we're looking at the differential amplifier, we've also got to worry about Q3 because it's attached to the, well, the resistor that biases Q3 is the same resistor which is Q1's load. So it's not easy to separate them out. In fact, there is a resistance looking into Q3, it's input resistance. And that input resistance in a small signal model will turn up near R1. So we have to make sure that we consider the two together. Or if we're not going to consider the two together, we must remember to bolt them in just the right way so that we take account of their interaction, even if we want to consider them separately. So I'm going to consider them together because I think it makes a more together picture. With regard to Q2, if I was a small signal here, a small voltage change here, I am trying to get to ground, and I've just come from this way, so we'll assume I'm not going back. When I look into Q2, what kind of transistor am I? Does it say on the slide? Oh, it does say on the slide. No biscuits was on the slide. So the signal sees the emitter of Q2, and its base is grounded, so it's common base, which is why I spent a couple of lectures going through all the different transistor circuits, because we have to talk about them now. So not only do we have to worry about the input resistance of Q3 and what its effect on R1 is, we have to worry about the resistance looking into the emitter of Q2 and what its effect on the signal on the emitter is. So we can develop a small signal model. So we've got, this is Q1, which is RB and G and EEE. This is the tail resistor. So this is the resistor there, that one. It appears connected to the ground. Why does it appear connected to the ground?
It's a negative source, and which goes to a negative source.
Yes. If you didn't hear that, the power supply is a battery, we'll just assume. And battery is a Thevenin source, and there is no internal resistance in this Thevenin source. So when the signal hits the negative rail, it can go down easily and then go through a battery into the ground. I can show you a mock-up of this, which we'll look at a bit later, if I dare to upset Addo. So this is a push-pull stage. We'll look at it in a bit. If I was a signal here, I can get to ground via that route, going through this transistor and through that power supply, or I can go up here and through there. And if you've been in the amplifier lab, you'll know why that's significant. If not, it doesn't really matter because there's no marks available for the lab. You just have to turn up. It doesn't matter if I give you the answer. Really, the trick with the lab is to learn how to use the kit properly. It doesn't really matter what we teach. So RE turns up connected to the ground. Everybody happy with that? If you were in EEE118, then it's the same reasons that I gave in those lectures as well. RE2 is the resistance looking into Q2's emitter. R1 is that resistor, and RE3 is the impedance looking into this base emitter junction on Q3. So that's how the circuit is developed. Everybody happy with how I came by the small signal model? If not, say now, because all that follows is a bit of maths. And the development of the circuit is the important bit. I trust you can all do maths. It's so long since I did the maths that I can no longer do it. Any questions on this at all? Right, in that case, I assume full understanding, except for the guy asleep over there. Anyway, if you work through this, now when I say if you work through this, it makes it sound easy, so I worked it through for you and I give out, anybody not got this one? Alright, I know who this is. Was it you? This is what you got. So I worked through it for you. I'm not going to do it now because there's nothing to be gained by me standing and reading equations. It turns out that V out 1 divided by V in is minus GM1 times the parallel combination of R1 and RBE3 divided by 2. Of course, it depends a bit on your assumptions. In the written out handout I give you, I made some assumptions and I said what they were along the way. But if you make different assumptions, you get a different answer. Doesn't mean the answer's wrong, just means the conditions under which it's right might be a bit variable. There's no point in learning what's on the sheet. It's not going to come up in the exam. And the reason for doing it is to get the hang of the method, nothing to do with the actual equations. So we like the biggest voltage gain we can get, differential voltage gain. And we can do that by making R1 and RB3 really, really big. And the reason is they appear on the top, along with GM1, so the bigger I make this fraction, the numerator of this fraction, the bigger my gain ought to be. And you might be thinking, oh, well, we'll make GM1 bigger as well. Sounds like a reasonable thing to do. Unfortunately, GM1 is EIC1 upon KT, where IC1 is the current that flows in that resistor there and into the collector of Q1. And if you want to increase GM1, you've got to increase IC1. And that means to increase IC1, you're going to have to decrease the value of this resistor. And the reason is you've got to have 0.7 volts across that. And if you're going to put a bigger current through it, you've got to have a smaller resistance to keep your 0.7. You've got to have your 0.7 because this base emitter junction is there, and it's going to try and force the 0.7 if you transistor in its forward active region. So to get GM1 bigger, you have to make R1 smaller by just about an amount to make the overall effect no change. So you can have a bigger quiescent current in your differential amplifier if you want to, but it won't change your gain. It does other stuff to do with frequency dependent effects, which we'll talk about later on in the course, but you don't get any advantage with gain. The input resistance, so I'm looking in the input of the first transistor. This is also by analysing the small signal circuit. It turns out that it's RB1 plus beta1 plus 1 times RE2. And if you go back to the common emitter amplifier, which has degeneration in it, so that was first or second lecture, I spent a long time talking about putting an emitter resistor in and how it was a good idea in some cases. That's the same result. So that derivation applies here as well. I'm not going to go through it, but it would be a good idea if you looked at the, I gave a paper handout, it's in there. Not the paper handout today, the paper handout, original paper handout. So if IC1 and IC2 are equal, which they ought to be, this is the two currents which flow down there and down there. They're equal, which we like. We get balance in the differential amplifier. And beta 1 and beta 2 are equal as well, which is very unlikely because beta is extremely variable, even within a production run, same day, same machine, same wafers, same everything, there's still a big spread of beta. But if this is the same, Q1 and Q2 are balanced and identical, and the input in resistance just looks like 2 times RB1. That's enough differential amplifier. Any question on amplifier before I carry on? Need time to digest it, maybe. Speaking of digestives, who's got the biscuits? Ah, I have. Good. Look after those. So I just wanted to make the digestive joke, that's all. Let's talk about voltage amplifier. This is a non-degenerated common emitter circuit. So this is, considering where we've just come from, extremely simple by comparison, because we've seen this earlier pretty much without any changes. We've got a small signal model composed of a transistor and RL, which is there. And RL connects to ground because VS looks like a good path to earth for a small signal, because the small signal just goes through the power supply and end up in the ground or in the VS minus. And if we look at the circuit on the prior slide, we had V out 1 was the final output. And it was the 0.7 across the resistor, plus V out 1, which is a small change from our last small signal model. And that goes across RB, which is the input resistance at this stage. We don't have to worry about any RS. Usually if I've got a source like this one, I'll say, oh well, there's a little resistor in there, and I'd call it RS, and I'd worry about what effect RS had on the gain and all that. But we know there's no RS, because in our last small signal model, we included RB, so it's already all bound together nicely. RS is 0. That's pretty much all there is to say there. Happy with this? If you're happy with the common emitter from 118, you're happy with this, because it's the same thing, without degeneration. So what should the gain be? Well, if you look off this node here, we've got several things that I haven't included on that diagram, the small signal diagram. The reason I didn't include them is I'm about to neglect them, because I know I can, and it makes the diagram look nice. We've got a little RCE across here, which is the early resistance for this transistor. It's the resistance in the model that gives you the slope lines of the output characteristic. Yeah? No. Early resistance. Come on. Quick show of hands. If you want, you can all close your eyes, I don't care. Anybody unfamiliar or familiar with it? So you should all answer. Anybody unfamiliar or familiar with it? Ah, come on. Right, early resistance. I don't mean to go and be bloody hard work today. Assuming a similar test setup where I look at VC and IC, and I'd have output characteristics of VC, output characteristics look like this, and I would have a range of either VBE or IB, and the slope of these lines all come back to a common point, and they all cross the x-axis somewhere. If I can fake it, maybe. Yeah, it's like somewhere over here, isn't it? They're not curvy enough. Anyway, this voltage where they all cross the axis is together. One big voltage there is the early voltage, and it's usually a couple of hundred volts for a decent transistor. And it's when we do the small signal model, we will put in a. I get rid of this. We put in a resistance. This will be our RBE, GMVBE, and then there'll be a little r, little c, or little r, c, e. And this resistance, essentially this is the Norton source. This resistance, the effect of it is to make those lines slightly curved and give you an early voltage. That's not RL though, but it's in parallel with RL on the screen. We've got the input resistance of, I'm going to get arrested at this rate. Input resistance of this transistor and the input resistance of this transistor, RC across there, and we've got the value of this resistor, all seen by a signal trying to get out of this collector. But we can get rid of almost all of them except for RL. And the reason is that RL is the smallest by far. RC is usually in the order of a couple of hundred kilo ohms. The input impedance of the two transistors in the push-pull quite big as well. So it all boils down to what in this diagram is called RVA. That one there. So if we do some standard analysis, we've got VA, which is output, is I out times RL, and then you sub in GM3 VB3 because that's what I out is. And the reason that's what I out is because there's only one, there's a loop here, and if this is a current source and there's only one loop, whatever this current is must be the same as in this current source. There's no other chance of any current appearing or disappearing. So I out must be GM VB3. So you sub the 3 and 4 together and you get 5, and then you've got to remember that VB3 is just another name for V out 1. If you go up to the small signal model, see I draw them together? There, they're the same thing. So that means that V out is GM3, V out VO1 RL, and you just rearrange it to get the gain, which is V out over VM. But they're not called V out and V in, they're just called slightly different things. And no surprise, it's GM minus GM3 RL. So this is the same answer as for a non-degenerated common emitter. And for a resistive load, so for RVA in the big diagram is a resistor, we are looking at a couple of hundred, probably. There are all sorts of tricks you can use to make it much bigger, but we'll talk about it in a bit. You okay? You okay? Question or no? Oh, okay. Everybody happy with voltage amplifier? Everybody disappointed to be still alive? You know, I really enjoy this. This is my favourite bit. There are all sorts of other bits which are interesting too, but this is my favourite bit. So, output stage. This is the business of this stage is to deliver extra current. More current than you can get from just looking at the collector of this transistor here. If you wanted to know how much current you could get off that node, you'd have to work out what the resistance looking into that node was. And you'd probably find it was approximately the value of this resistor, because you'd end up making all the same assumptions I made earlier when I did the gain analysis. And that resistor is actually quite large. So big output impedance, big output resistance can't deliver very much current. So we want something to amplify or allow a bigger current. And the signals we're looking at here are large. That is to say, we cannot draw small signal models. Well, okay, you can draw whatever you like. I don't care. But if you draw a small signal model, it won't do you any good. So there's no point. We have to worry about the 0.7 and the signal together, which is come back to what you were asking earlier, your initial question about what happens if the signal's so big it turns off the differential amplifier. Now we're in a situation where that's going to happen. So Q4 will take charge of the positive, or not take charge, sorry, will deal with the positive half cycles, and Q5 will deal with the negative half cycles. And there will be situations where the one transistor is off and the other is on, and then the first one is off and the other one's on. So we will not always be in the forward active region, and that's why you can't draw small signal models, or it doesn't make any sense to. Another way of thinking about it is that there is a quiescent current that flows from Vs plus to Vs minus, and that quiescent current will be the same order of magnitude or less than the signal currents which are passing through this circuit as well. When we were in situations in the differential amplifier and the voltage amplifying stage, and in the common emitter stuff we did in 118, we always had a situation where we had a quiescent current which was nice and big, and there were signals on top which were small. Now we're in a situation where that doesn't hold, and that is another way of saying you can't draw a small signal model. So the voltage gain of the output stage is approximately unity. So why is that? Could be the last biscuit of the lecture. Emitter follower. There we go. Just in case you didn't catch that, both these transistors are emitter followers. As a consequence, their voltage gain is about 1, slightly less than 1 actually. If you're unhappy with that, it's in the prior lecture and it's in the handout I gave out as well. So the objective of the output stage is to increase the voltage amplifying stage's ability to put current in the load. And the combination of the voltage amplifying stage and the output stage provide the power gain, because we've got voltage amplification and current amplification, so the power is volts times amp, so power's going up. Now call it voltage amplifier stage, but don't forget the differential amplifier has a non-unity gain which is often bigger than 1. It can be smaller than 1 as well, and there might be some reasons to do that, but I don't want to get into it. So Q4 and Q5, these transistors must be turned on by the signal. They will not be turned on by the biasing unless we decide to bias them. So in the circuits on the chalkboard or top of the lecture, they will not be turned on under normal circumstances where there is 0 signal. So that's why I said we'll assume 0.7. Actually, that's a lie. And that's why you can't have a magic box here. We will eventually find a magic box to put there. But for now, no signal conditions, Q4, Q5, both switched off. No quiescent current at all. A result of the signal needing to turn on the transistor is this crossover distortion. And if you've been in the amplifier lab, blah, 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 you've seen it. And it looks from a textbook a bit like this. Actually, I stole this from a simulation, but I very cleverly manipulated the transistors, even if I do say so myself, to be identical and like they dropped out of a textbook. So this is not a real waveform. You will not be able to get this on a scope, from a physical circuit. But it's what you will see in a textbook, so to be consistent. So we have Q4 is on, Q5 is off, no current. Q5 is on, Q4 is off, no current in Q4, Q5 no current. So we're driving this with a sine wave. And there are these little flat bits. And that's when neither transistor switched on. If you want to know what the output voltage looks like, well, the load on the output is a resistor, so you just multiply that by a resistance and you get a signal that looks the same shape. So I didn't bother to draw the output voltage. Question? Yeah. We like to get rid of this crossover distortion. But before we have a go at that, I want to talk a bit more about what happens when you bias this sort of stage. We can bias the transistor to lessen the effect of crossover. Essentially, we're going to try and provide the 0.7 it needs, and we'll try and provide this 0.7 that this transistor needs. Now, if we want lots of current, you'll have to go a long way above 0.7. The signal will deal with that, because the signal is large. We want to provide just enough so the transistor's turned on, so you don't get that little flat bit. But to show you some differences in how you can bias this stage, which are relatively well generalized, you can talk about Class A, Class B amplifiers, which are this shape and different shapes, with gain, without gain, voltage or current, or that sort of thing. So for the thing that I've just shown you, we actually have slightly less than 180 degrees angle of conduction. And the angle of conduction is, for one of the transistors, how long it's on for as a fraction of the whole cycle. So the whole cycle will start halfway between this flat bit at 1 millisecond and go towards 2 milliseconds. I don't know. If you're going to let your phone go off, it's generally accepted that you sit at the back. Never mind. You should have talked and asked me if I want a biscuit. So, angle of conduction slightly less than 180. Happy with the idea of angle of conduction? I'm going to take that as a yes. Let's have a look at several different sets of biasing. So this is actually almost ideally biased. The flat bit is gone. So I've turned on both transistors just enough so that there's no flat bit. And if you look at the low voltage, you'll find it follows the current waveform, so it looks nice. Now, this is imperfect, but looking at this graph, we just can't see it. If we had lots and lots of data, take a Fourier transform and look at the frequencies that exist, we would find there is some non-linearity in the circuit. We put in 1 kilohertz, we'll get out 1K, 3K, 5K, and the components of the 3K and the 5K and so on and so forth will be small, but they will be there. Very difficult to get rid of them completely. Very difficult to totally eliminate crossover distortion. But we can say the angle of conduction is almost 180 degrees, assuming that I've trimmed it just right. If we keep turning up the bias on these two voltage sources, that one and that one, we can go to the point where actually each transistor is almost not turned off at all. There's a small region in the middle here where Q4 is off, and there's a small region in the middle here where Q5 is off. And I put the current in the load as well, and you can see that as Q4 turns off, Q5 is turning on by just the right amount to keep the current in the load looking sinusoidal. I like that, that's very clever, I think. I haven't done anything special, I just biased both transistors a little bit more on. If we keep going with this, so this is conduction angle of more than 180 degrees, because we say I was conducting from about there to about there. That's more than half a cycle. Only a little bit more though. But if we keep going, we can end up in a situation where both transistors don't actually switch off at all, because this is the zero current line. We've still got about 0.8 milliamps, even at the lowest point. So there's a large region, 360 degree conduction of this transistor and 360 degree conduction of this transistor. So we've arrived at class A. That's just a name for it. If you look in a textbook, they'll say class A plus B plus C. Goes all the way down to J, and then there's an S and a T. We only talk about A and D at the moment. So this is still the waveform in the current waveform in each transistor is not sinusoidal. There's still a bit where it's sort of getting towards turning off. If we keep going with the biasing, we can arrive at a situation where the low current is sinusoidal and the currents in both transistors sinusoidal, almost sinusoidal as well. And if I kept going more and more, that would just become more, everything looks like sinusoid. So the question of angle of conduction is really just another way of saying, what's the quiescent current? If I turned off the sine waves and I looked at this diagram, I'd have a line there, which is the current in Q5, and I have a line here, which is the current in Q4. And these lines are both above the maximum current I ever have in the load, just about. The load current would be zero under those circumstances. If I went back to the class B bit at the top here, if I said what's the current if there's no signal, well, this is all to do with signal. So there are 3 lines on 0 and nothing more. So how much I bias those transistors on determines the quiescent current. And the more I make the quiescent current bigger than the signal, the smaller the signal starts to look. And I'll transition from a large signal arrangement into a smaller signal arrangement by virtue of the quiescent current becoming much bigger than the signal. So this is how the quiescent current and the class of the amplifier and the angle of conduction all bound up together. Now I have no minutes left, but I can show you a quick simulation how I generate those sort of waveforms. If I run this is my class B bit. as my less than class B. But if I run this one now and delete that one, we can see them all together. Now we've only got two colours, which is a bit crappy, but these are collector currents. So my less than nothing is in the middle with a flat bit. Then I've got the quite well tuned bit. Then I've got the class A with quite low biasing, and then I've got class A proper. I will put the simulation up with the lecture notes, and there is some discussion as to how you download the software and that sort of thing. Righty, I don't know when I'll see you next, but we'll carry on from there.